So let's go over this summative assessment. Question number 1. This is a trick question. An electron is traveling in a region of uniform magnetic field. At the instant shown, the electron is moving parallel to the field direction. Now this is a trick question because the field direction and the electron flow must always be at 90 degrees. If they're not at 90 degrees, the sign aspect of the equation BQV makes the answer 0. Okay, so you just have to remember, I think we did this in one of the formatives and you seem to do okay on it, but just be careful. 20. The gravitational field strength at a point X in a gravitational field is defined as the force per unit mass on a small point mass placed at X. Okay, so be careful choosing the correct definition. You must learn your definitions before we have summative tests. Question 3. The current in two parallel wires I and 3I in the direction shown in the diagram below have a force F acting between them. Now what this means is that the total force combined is F. But listen to the wording. The magnetic force on wire 2 due to wire 1 is F. The magnitude of the force on wire 1 due to current 2 is... Now this is the wording in Newton's third law. Right? Equal and opposite. So forces that act are always equal and opposite. Now what this means is that if there is a force of F acting on 2 by 1, then there must be an equal and opposite force of F acting on 1 because of 2. So the answer is C. Two particles, X and Y, are attached to the surface of a horizontally mounted turntable. The turntable rotates uniformly about a vertical axis. The magnitude of the linear velocity of X is V, and the magnitude of its acceleration is A. So we're talking about X, V, and A. Which of the following correctly compares the magnitude of the velocity of Y and the magnitude of the acceleration of Y with V respectively? So if we imagine this is a plan view of this, we have X and we have Y. Now as they spin, the time that it takes X to get around once is the same as Y. Okay, so their period is the same. So if we compare the velocity of X, which is 2 pi r over t, to Vy, which is also 2 pi r over t, only this time r is bigger and t is the same. Because you are dividing a larger number by the same number, your value of velocity is greater. So the answer so far is either A or C. Now, the acceleration. What is the relationship between velocity and acceleration? Well, the quickest relationship is this one. And as you can see, acceleration is proportional to the velocity squared. So if your velocity is increased, then your acceleration has increased as well. So your answer is C. The diagram shows a current I in a vertical wire that passes through a hole in a horizontal piece of cardboard. Draw the magnetic field pattern. Now you've got to be careful because it's 3 marks. So what we're looking for is shape, direction, and strength of field, which some of you missed out on. So very difficult to draw with this software, but I'll try it. The diagram should show, firstly, a radial field, so you've got circles. Secondly, the direction, which is using your right hand, and your fingers curling out that way. Oops. I meant, of course, curling this way. Okay. So you're going up and we're curling around this way. So therefore your direction is this way. And then your third mark is that you show that the distance should be getting bigger. So I haven't done a very good job of it here. Let me try it again. So this is a little bit better. So what we've got is this one goes round and you've got your direction, you've got your shape, and now thirdly you show that the distance between the field lines is getting bigger. So this one should have a bigger distance than this one, and then this one and this one. Okay, so you have to show that the field strength is decreasing as we go further away from the source. Okay, so let's continue. The diagram shows a length of copper wire that is horizontal in the magnetic field of the Earth. The wire carries an electric current and the force of the wire is shown. Identify the direction of electron flow. So this is using your left hand rule. Okay, so using your thumb pointing upwards and your magnetic field strength this way, you should end up with a current flow, a conventional current flow in this direction. Part 2. The horizontal component of the magnetic field at the position of the wire is 40 times 10 to the minus 6 Tesla. Now, it tells you about the mass per unit length. You should always be suspicious of information that's given like this. You're given the mass per unit length, 1.41 times 10 to the minus 4. Why are they giving me mass per unit length? Let me just put a question mark there and see if it's useful later. The net force on the wire is 0. Now, why are they telling me that? Let's see if that's useful as well. Determining the current on the wire. Now, I always recommend writing the units that you do have above, because if you start to see B above the magnetic field strength and you see an I there, you should psychologically start like compiling like formulas in your brain. You should say, oh, BI, maybe this formula would be useful. Now, we don't need this because there's no angle involved, but we definitely need Bill because that will give you the force acting. But wait, it says the net force on the wire is 0. Right, now what are the forces acting on this wire? We have the force up, which, if it was on its own, would accelerate upwards. But the wire's not accelerating. The wire has no net force. So there is another force acting down. And what is that force? That force is weight, which is mg. So at the moment, what we've got is that BIL is equal to mg, right? But we don't have length. And we don't have current. But what are they? Let's go back to this big question mark. But they've given us the mass per unit length. So if we rearrange this to give us BI equals M over LG, so we bring L over here, we've got mass per unit length in the formula. And do we have the mass per unit length? Yes, we do. It's 1.41 times 10 to the minus 4. So no piece of information is useless in an IB question. In fact, it's giving you a bit of a hint about where to go. So the current then would be equal to the mass times the magnetic field strength times the length times G. And if you substitute all those values in, you should get a current value of 35.25. Please try it now if you did not get this correct. In 1798, Cavendish investigated Newton's law of gravitation by measuring the gravitational force between two lead spheres. What is Newton's law of gravitation? Well, what you need to do is put in words the following. Force is proportional to, so you have to say that word, the product of the masses over the distance between them squared. So all aspects of that definition unnecessary. Now, a student repeats the experiment with modern apparatus and has lead spheres of unequal size. The large sphere has a radius of 100 millimeters, so we're going to write that in meters just to make life easier, and a mass of 47 kilograms. The small sphere has a radius of 25 times 10 to the minus 3 meters and a mass of 0.73. Why do we need to do it in meters? Because our gravitational constant includes meters in its definition. So you have to change everything to meters. Estimate the gravitational force. Well, it's no coincidence that they've asked us about Newton's law of gravitation. So we use F equals G m1 m2 over r squared. What distance are we using? Well, we assume point masses. So the center of each mass is the distance that we consider. So we basically need the distance from the two centers of those spheres. So 25 times 10 to the minus 3 plus 100 times 10 to the minus 3 squared. Then you have your G constant and your two masses, 47 times 0.73. Okay, and don't forget, I know I've said it already, but don't forget your gravitational constant. And your answer should be 1.46 times 10 to the minus 7. Now this last question was quite challenging, so let's work through it. A student repeats Cavendish's experiment using lead spheres with twice the radius. Discuss the effect of on your calculation. Now if we think back to our calculation, G equals m over r squared. Most of you managed to figure out that if you double the radius, your final answer would be 4 times smaller. So I gave you some credit for that. But there is a little bit more to it, because if it has twice the radius, and of course this is a bit of an assumption, then assuming they're made of the same material, then the mass of the spheres would change as well. Now, what's mass? Mass equals density times volume, right? So what is the change in the volume? Well, the volume of a sphere is 4/3 pi r cubed. So if we double that radius, what we end up with is a mass which is 8 times, it's 2 to the power of 3. 2 to the power of 3 makes 8 times bigger. So 8 of one mass times 8 of the second mass, which again has double the radius. So you would end up with 64 times the mass square, or the mass product, and 4 times smaller because of the radius. So in the end, the final answer is 16 times bigger, right? So what I did to try and adapt to the fact that was a bit too challenging. Well, it's an IB question, so you could get something like that. But I made this out of 3. I was hoping that maybe some of you would see that mass connection, and I would have rewarded it generously. Okay, so anyway, that's the end of that paper.